Okay, in this video I'm going to talk a little bit about homework number 8 for our physics class. This is in unit number 3. I think a lot of the questions are pretty straightforward and we're just going to be using formulas from our formula sheet, but in the event that there's something a little bit more complicated, I'll jump over to my sample solutions and let you take a look at that. In problem number 1, we're being asked to find the mass of a large ship that has a momentum, remember we call that P, of this quantity, and when the ship has got a velocity of 48 kilometers an hour, we should be able to compute mass, because we'll note that momentum is equal to mass times velocity. What I want you to be on the lookout here for, though, is that the velocity is given to us in kilometers an hour, and every time we use a formula from our formula sheet, we really should be using an SI unit. Kilometers per hour is not the SI unit for velocity, so make sure that you make that adjustment before you use the formula. In question 2, we have a bullet that's accelerated down the barrel of a gun, and it was the combustion of the gunpowder that did that. Apparently there was an average force exerted on a 30-gram bullet to accelerate it to a speed of 600 meters per second, and it took 2 milliseconds to complete that task. So I think the assumption here, since we're talking about a bullet in a gun, its initial velocity does need to be 0, and we'll use this velocity down here as our final velocity. And then also, while the mass is given to us here, we need some number in kilograms, because that's our SI unit. And since the time that it takes to complete this activity is given to us in milliseconds, we need that in some sort of quantity of seconds. So we've got a couple unit conversions to work with. And then the formula that I think would be important here is the notion that a force times a certain amount of time, or a change in time, is also equal to our impulse, or change in momentum, or mass velocity final minus mass velocity initial. And I think working with that description should be sufficient for solving this question. So I'll let you work at that one. With problem 3, again, pretty straightforward. We have some given information, an average force, a duration of time, and we're being asked to calculate impulse. So again, impulse is equal to the force exerted over some change in time, or for some unit of time. So we can use that for part A. In part B, if we're looking for the final velocity of the bumper car, if we know its initial velocity and the driver's mass, that's the mass of the driver and the car. With that information supplied, I think we'd be able to work with it pretty easily here. Again, impulse, which is our change in momentum, which is our mass velocity at the end, minus our mass times velocity at the beginning. All of that is still equal to some force that we apply over some unit of time. Your job, of course, would be to find the final velocity, VF. Now, don't be surprised if you see negative numbers in any of these results, because impulse and momentum have direction to them. We have forward and backward motion all the time, so positive and negative quantities is pretty important. In question number 4, the problem's asking, why would a 10-meter fall onto concrete be more dangerous than a 10-meter fall onto water? Well, I think it's important to note that if you fall 10 meters onto either one of these, the amount of force at impact is going to be the same. So the force onto the concrete versus the force onto water would be exactly the same. So it's not that the force is any different, but think about how the impact goes when you hit concrete versus when you hit water. Part of our discussion this week has been how force and time are related and how those combine together to create a new quantity. Which one's going to create more of this impulse, and which one's going to create less impulse? And is it a good thing to have a big impulse or small? Now even that's a little bit of a loaded question because, truth be told, the impulse when you strike the concrete is going to be the same as the impulse when you strike the water. But how that impulse is generated can be different. So let me just remind you again that impulse is the change in momentum. So in both cases, your momentum is changing from some velocity before you hit the water to 0, or some velocity before you hit the concrete to 0. So the amount of change in momentum is the same. But another way to think about impulse again is multiplying a force times time. Force times time. Now if the product of force times time has to be the same, the force impacting the concrete versus the time that it takes to impact that concrete, and the force as we impact the water compared to the time that it takes to impact the water, might have a different arrangement to them. So you might recognize that the amount of time that you're in contact with the water during this impact is greater than the time that you'd be in contact with the concrete. And if the time component increases here when we're impacting the water, then the average force over that time has to decrease. While the time that we're impacting the concrete, since that's so small, the amount of average force ends up being much larger. So while the force at impact of the concrete and force at impact of the water might be the same, during the impact the amount of forces change, and this is that force kind of spike that we were talking about in lab this week. Now that's a lot to think about, but if you can imagine, if the amount of time of the impact is much larger and the amount of applied force, average force, ends up being smaller, then I would much rather jump into a pool of water than into a pile of concrete. And that's part of the reason why. We can increase the time for the duration of that impulse, and that makes the perceived force much less. And in question number 5, we're given a graph to work with here, and we're measuring the amount of force that's being applied to a golf ball. Now this is just the horizontal component of force. It's not the entire quantity of force here. So we need to be aware of that. There's going to be some sort of vertical component of force that's applied when a golf ball strikes, or sorry, when a golf club strikes a golf ball. But what's important to note is that we have a y-axis that's measuring force and an x-axis that's measuring time. And as we've noted in class so far, if we have newtons measured along the y-axis and seconds measured along the x-axis, we would convert from milliseconds to seconds, and that'd be fine. Well, we have those two quantities, then the area underneath the curve ends up producing a unit known as a newton second, or a quantity of impulse and momentum. So our job here is to effectively find the area under the curve. If this was a true curve, we would require calculus to find that result, but since this curve is nice and linear in 2 dimensions, we can use regular geometry to find the area to represent our impulse. So we'll say for part A that the impulse is equal to our change in momentum, which is the area under the curve. Similarly, in part B, since impulse is the change in momentum, we can report it as mass times velocity final minus mass times velocity initial. And if we have the area under the curve representing impulse from part A, and we know the mass, let's see here. Yes, we do know the mass of the golf ball. It's 46 grams. Right, we have the mass of the golf ball. We know that it started off with a velocity of 0, and that would allow us then to find our final velocity for part B. So I think this is a good stopping point for this part of the video. Questions 1 through 5 have most of our discussions with impulse and momentum. As we get into number 6, while it does have something to do with impulse and momentum, it's more about collisions, elastic and inelastic. So I'm going to stop this video right now, and I'm going to record a second one while I talk through the remaining questions. Thanks for watching.